Swayam Prabha. Digital India. Educated India.
So welcome again to the new lecture of the course, properties of materials. So let's just begin, let's just start with what we did in the, where we were and what we did earlier. So what we did was we looked at the role of dislocations in making slip to happen, and this is basically by dislocations reducing the stress required. And you saw that if you have a crystal like this, okay, and when you apply shear stress to it, then it sort of takes this shape, but this microscopically speaking, if you look at it, then this basically happens by looking at by having the slip occurred in the crystal. So if you look at how the steps are formed by, let me just show you. So essentially you have one crystal like this, okay, then the next crystal could be something like this, and so you sort of create these steps which are microscopic steps formed as a result of slip between successive planes. I am sorry if I am not drawing it very well, but basically I hope you get an idea. Okay. So these are the sort of, you can say, the slip steps on the surface due to motion of successive planes of atoms over each other. So atoms have, so when the dislocation moves from one part to another, it causes the formation of the step on one side, and this leads to, and when you look at it microscopically, you tend to form many steps. So in order to visualize this, let me show you a sort of PowerPoint presentation which can help you understand what is this slip looks like microscopically in the real crystals. So this is these are certain photographs which have been taken from doitpoms.ac.uk. So let me just show you the. So if you look at this crystal, this is a cadmium crystal. So this is taken from doitpoms.ac.uk from University of Cambridge website. So you can look at, there is a whole module which you can look at there. So this is the undeformed crystal when looked at under the scanning electron microscope at certain resolutions. So you can see that this scale bar is 100 micron. So this whole thing would be about 15 times of this. So it's like 1.5 mm thin wire. So when you start deforming it, this is a deformed cadmium single crystal. When you start deforming it, then you can see you form these steps on the surface. So these are basically, so you can see the steps here on the surface, you can see the steps here. So these are basically, you can say, the slip steps which have formed because of slip of atoms against each other in successive planes in the slip plane. Of course, the slip has to occur in the slip plane. So you can see this is what is happening. If you look at it microscopically at a further high, so this magnification, you can see that here its scale bar is 100 micron. Now if you increase the scale bar, if you increase the magnification, reducing the scale bar to 5 micron, you can see that these are the microscopic steps that you form on the surface of the sample. So this is what basically, microscopically speaking, slip phenomena is. I'll show you a video of how does it happen. So, let me just show you the videos of the slip, the microscopic phenomena of slip when viewed under scanning electron microscope live. So, this is one of the videos. Again, these videos are taken from doitpoms.ac.uk University of Cambridge website. So, if you look at this, for example, so you can see that this is the crystal which is being deformed, and you can see formation of these steps on the surface of the single crystal. So, you can see very clearly that steps are forming on the surface. It is very visible. And this is another video which shows you how does it happen until fracture. So, you form the slip planes, and then you have this formation of a neck followed by fracture. So, this is a beautiful example of how the slip happens, and of course, you can see that. So, this sort of replicates what you saw in engineering stress strain curve. You form a neck. So, this is where instability comes in, and then it leads to fracture. So, this is basically, it replicates what we saw in engineering stress strain curve, that you form a neck followed by fracture, which is basically ductile fracture. So, this is a microscopic examination of basically how the slip happens. Now, what we are going to do now next is we are just going to look at some of the quantitative ways of defining the slip. So, essentially what we are saying is that slip, just to summarize this part, plastic deformation is caused by slip of atoms against each other on slip planes along slip directions. Okay. Second point is, for slip to occur, your resolved shear stress has to be more than critical resolved shear stress. Okay. So, it is a function of yield stress and orientation. So, only when your yield stress and orientation are such that the stress applied is such that you are able to exceed this CRSS, then only you are going to be deforming. Now that you fulfill these two conditions, the value of experimental stress is lower than value of theoretical stress, and this is because slip takes place with the assistance of dislocations. So, dislocations, and hence tau experimental is lower to cause plastic deformation. So, this is sort of a summary of what we have done over past few lectures. Now, what we are another way of visualizing this slip is, so the slip can be visualized by visualization. So, when we say the slip takes place by, you have formation of, let us say you have a plane of atoms, you have an extra plane here, another plane there, and then when you apply stress to it, then this moves further up, and eventually as you keep applying the stress, this dislocation, which is this extra plane. So, let me depict this extra plane here, and this eventually moves out of crystal, giving rise to formation of a step. So, this is the dislocation movement which is taken out. So, this is the step that we create, and this movement can be sort of seen by caterpillar kind of movement. So, let us say at this position, if you have a caterpillar, the caterpillar shows a hump like this. When you apply stress, the hump moves forward, and when you apply stress further, the hump is in the forward direction, and before it becomes, at this point it will become flat basically. So, the caterpillar is going to, it is going to be like this, then it is going to move like this, and then it is going to move like this, finally it becomes flat. So, this is you can say hump on caterpillar back. So, it goes from here to here, here to here, here to here upon application of stress. This is another visualization that one does. So, what we have said is that the theoretical strength is high, and but practically the stress required to cause dislocation, to cause plastic deformation is lower because of stress. So, what it tells you in other way is that if you want to increase the strength, if you want to enhance the strength, then one of the recipes is going to be to remove the dislocation or defects, and this is what basically we do in something called as whisker. Whisker are basically, you can say, hair like material forms. So, very thin like this. So, just like hair follicles, and these are extremely thin, of the order of, let us say, a micron or lower, a few microns, let us say, or lower. So, when you reduce the dimensions of a material to this small, so reduction in dimension causes defects to reduce in number. So, as a result, in whiskers it is like nearly defect free. You can say it is basically a defect free crystal. So, when it is a defect free crystal, if you conduct, for example, stress strain test. So, this is a stress strain test on whisker, and when you apply the stress, basically you go to a value of nearly, so let us say this is stress strain curve on whisker. So, you reach a strength of the order of, let us say, 700 MPa, which is close to 1 GPa, very high strength, and then when you reach very high strength, you are able to break some bonds, and at this point you introduce a defect or dislocation, and this is where there is a sudden drop in strength. So, basically you can say whiskers are defect free crystals whose dimensions are about a fraction of micron thick, and whiskers are generally used for, so they are very strong and hence used as reinforcement to make strong composites. So, they can be blended with, let us say, polymers or ceramics to make them strong, very strong. So, this is the idea of use. So, basically what we have said is that real crystals in bulk forms have dislocations, and if you reduce the dimensions, you lower the dislocation density to the extent that you can eliminate them, and then you make what we call as whiskers with high strength. So, this is the converse of what we have. Now, what is the quantitative way of estimating this kind of strain? So, the resolved shear stress that is required needed to cause slip via dislocation motion. So, this depends upon two factors. one is width of dislocation, second is the magnitude of Burgess vector. So, basically what we mean here is, what do we mean by first of all width of dislocation thing. So, let us just make a schematic drawing. So, let us say this is a atomic plane, another atomic plane, okay, and let us just draw a few of these these are the, let us say, atoms, and then we have somewhere around, let us say we have so the way we connect these is, so we have this, so we have these connected as this fashion, okay, and we have these connected in this fashion. So here connected sorry. And hang on. So, let me just make a little bit of, okay. Okay. So, these are, let me remove this one which is in between some, all right. So, these are basically, you can say, atoms sitting here, here, all the places. All right. So, the dislocation width is decided by, it is basically a function of bonding first of all, and dislocation width is essentially the region up to which you can see the distortion. So, this is roughly the dislocation width. So, this is the dislocation we have, this is the dislocation, and the core of dislocation. So, basically up to the point wherever you have stress field of dislocation extending. So, this is the width of dislocation W. So, basically dislocation, let us say we have edge dislocation. Edge dislocation will mean you have extra top plane, extra plane, let us say in top, okay, top side. If it is in top side, which means top side will expand and bottom side will contract. So, as a result, top side will face compressive stress and bottom side will have tensile stresses. Right, because this extra plane will try to push these here, and this, so this side the spacing, it will try to push the lattice apart. So, as a result of pushing the lattice apart, this region will undergo, you can say, compression. So, it will have compressive stresses, and this region will have tensile stresses. So, and this width of dislocation, so not only, so basically how far is the stress field is an indicator of width of dislocation, but width of dislocation is also, W is also a function of nature of bonding. So, generally covalent materials, covalent / ionic materials will have strong bonds, and as a result, so when the bonds are stronger, the extent, the region in which the bonds will get stretched and compressed is also lower. So, as a result you have narrow W, and if you have metallic bonding whose bond strength is lower, this will lead to weaker bonds, and as a result you will have higher or larger W. So, larger W, or you can say the wide region. Okay. So, basically and smaller the width is, more is the stress that will be required to move a dislocation. So, this dislocation width, so if you, so this is for example so you can see that this is the distortion, you can see that atoms are corresponding with respect to each other. So, whenever at the point at which they start becoming sort of normal, up to that point is the dislocation width. So, basically in metals which show metallic bonding and are ductile, they show wide dislocations. Okay. So, schematically speaking, you can say in a metal the scenario would be so, in the case of let us say metal, this is W. Okay. In case of ceramics or glasses, the scenario is something like this. So, this is W in case of ceramics. So, we can say W for ceramics in general is W for metals, and this means, and we will see the equation. Okay. And another thing is the Burgess vector. So, we will come to Burgess vector in a little while, but let us, so this the stress which is called as Peirells Nabarro stress or Pn stress, and this is given as tau Pn G into exponential of minus of 2 pi W divided by B. So, here G is the shear modulus, and W is the dislocation, let us say core width, and B is the Burgess vector, and W is also given as, W is approximated as A divided by 1 minus nu, where nu is the Poisson's ratio and A is the lattice parameter. So, this is how, so basically you can see when you have different values of W, let us say, and if you want to measure the W Pn. So, for 0 W you can see that Peirells Nabarro will be G. So, which means this is the case when you have no dislocation. Okay. So, it will be same as the theoretical strength, essentially G divided by 2 pi if you approximate it. And if you look at, if W is equal to 1 Burgess vector, then this is G divided by 400 times. So, essentially just introducing dislocation has caused the stress to decrease by 400 times, and if it is 5B, this goes by G divided by 10 to the power 14, and if it is 10B, this becomes G divided by 10 to the power 27. So, basically this is an exponential function. So, of course, we do not drop the strength to these levels, but our strength is somewhere in between. So, this is the region in which most of the B value, W values are. So, basically we can see that there is a, and you can also see from this tau Pn will increase as W decreases. So, which means metal will have lower Peirells-Nabarro stress. So, tau Pn for metals is lower than ceramics. Another observation that we make is tau Pn increases as B increases. So, which means larger the Burgess vector, higher the Peirells-Nabarro stress. So, which means materials with larger B will have higher tau Pn. So, metals Burgess vector is smaller than ceramics Burgess vector. So, that is why it turns out that, so in case of, because the Burgess vector is going from one atom to another atom of same type. In ceramics, because they are ionic solids and they are not close packed, because the anions and cations have to, because the anions and anions have to stay away from each other because of repulsion. So, as a result, the Burgess vector in ceramics tend to be larger. So, if you want to go from, let us say, one type of an ion to another type of an ion, you have to go for larger distances as compared to than in the metals. So, that is why the Burgess vector in ceramics is larger. So, these are the two reasons why shear stress of to cause deformation in metals is lower than that in the ceramics. And then of course, we also saw that that using this expression. So, this expression tells you that the fact that you introduce a dislocation, your stress goes down by 400 times, and we are somewhere in between. The stress values are lower by 1000 times or at least 10,000 times lower than the theoretical values. So, the B values are generally between, the W values are between B to 3B or 4B, something like that, B to 3B. So, this is a generally dislocation cores are very narrow, and as a result, however, that is good enough to cause substantial reduction in the strength, and depending upon the magnitude of W and B, different materials will show different strengths. So, we will stop here, we are running out of time now. We will do the analysis of this little bit more in the next class before we move on to the strengthening mechanisms in metals. Thank you.